Hi there, and welcome to another episode of Study With Me. Today I'm going to be talking about special relativity, an area in physics that I have studied somewhat before, but I've kind of forgotten a few things and I'm definitely a bit rusty. So I'm going to just work through some concepts in special relativity, mostly an intro to space-time diagrams and some of the cool results that you can start to use those diagrams to discover. So whether you have studied this topic yourself before and want a bit of a refresher, or you want to learn some of these topics from the ground up, I hope that listening along to me talking about some special relativity will be enjoyable and to your benefit. So, like I said, I've studied special relativity before, and there are a few key things I do definitely remember, and I think I'm going to need to know, and that you'll need to know to progress a little bit here, and I've written them up on the blackboard. So let's have a look at some of our fundamental concepts that I know and hopefully use these to build a bit of a base to go on and get a better understanding of space-time diagrams. Now I remember those being a very cool aspect of special relativity, but I'm sort of hazy on the details of how they work. There are some words I remember like space-like and time-like, but I can't quite remember what those mean. So let's work up to that. Now the first really important point is that an observer is someone or something that makes physical measurements. So whenever we refer to an observer, that's what we're talking about. Second of all, your position in your reference frame is always 0. So we're going to talk a bit about reference frames here, and our observers are going to exist inside reference frames. Just know that the observer will always think that they are staying still, that their position is 0, and that everything else is moving around them. Special relativity is often credited as one of Einstein's, inventions, and we have some of Einstein's important postulates here. We've got two. And these really govern what's going on in special relativity. So one, the laws of physics are the same in all inertial reference frames. So an inertial reference frame is one where I guess Newtonian physics applies. It's a reference frame that is either staying still or is moving at a constant speed. Really, we're just not including accelerating reference frames, and I think this inertial reference frames is what makes special relativity special, as opposed to general relativity, which can deal with acceleration and likewise gravity. So that's the first one, that the laws of physics will be the same. And two, the speed of light in free space is the same in all inertial reference frames as well. Okay, so that speed of light is a constant when we're talking about inertial reference frames. So I think that's all of the important details that we're going to need to know. Hopefully some of them might be a bit of a refresher to you, and let's go on and use them to understand a few more concepts. I'm going to be working through the Special Relativity course on brilliant.org, so if you want to use the same course to follow along, you can sign up for free at brilliant.org/Tibees, and the first 200 of you that want to do that can get 20% off an annual premium subscription. Okay, so our first picture here is that we have a girl moving forwards on a raft, we have a guy in a balloon moving forwards, and we have a gull moving forwards as well, a seagull. Okay, so we've got three different reference frames here. In this girl's reference frame, she thinks that she's not moving, that the balloon is moving away from her, and that the gull is moving away from her as well. So, space-time diagrams. They can be used for something as simple as this problem that we're looking at here, even though no one is moving close to the speed of light, and this is really just classical mechanics here. For this diagram here, we have time on the y-axis and x down on the x-axis, which is position. So this blue line that is plotted here is the path of the seagull. The point that it intercepts is the initial position when you first started to observe it. This is all for the reference frame of the girl on the raft, and this diagram here is from the reference frame of the guy who was on the balloon, who was moving forwards at his own speed. This is how he perceives the gull. So we've still got time, and instead of x we just have x dash to be a new reference frame. It's still the position though. So this is Galilean relativity as opposed to, I guess, special relativity, because no one's really moving at a very high speed and observers agree on the time that all events take place. So the axis on the space-time diagram in this new frame is still just labelled t instead of t dash, because they're not going to agree on the exact position of the bird relative to them, but they will agree on the time. So we do have a question here relating to this diagram. If we are on the raft, and this is from the point of view of the guy on the balloon who's moving away from us, which is moving faster, the guy on the balloon or the seagull? Now we can actually tell the answer just from looking at this diagram here, even though it doesn't seem like we've got much information, and the answer is that the gull is moving away faster. And the reason that this is true is because this was from the point of view of the guy in the balloon, and the position of the gull was moving away from him. So if he's moving relative to the girl on the raft, and for him the gull is moving away from him, then to the girl on the raft, the bird is moving away even faster than the guy on the balloon is. Lines that are drawn on space-time diagrams are referred to as world lines, and they do encode quite a lot of information about an object that is moving. So we can actually get the speed that an object is moving from its world line. Slope of a line is the change in the rise over the change in the run, so that's dt over dx, change in time over change in position. In this case, that turns out to be 1 over the speed of the gull. So the world line is inversely proportional to the velocity, or the relative velocity. So that means the steeper the world line, the lower the velocity, and the less steep the world line, the higher the velocity. Now we're going to extend our examples to something that's referred to on Brilliant as relativistic laser tag. So in this game we're going to have two people, Alyssa and Bev, and they're practicing for a laser tag tournament, and they win by hitting the target on the other team with simultaneous laser bolts. So they both need to hit this target at the same time. They set up a target that's halfway between them, and they are at rest relative to each other. The target is also at rest in their reference frame. Their goal is to coordinate their firing so that their lasers hit the target simultaneously. They have a countdown, and then at t equals 0 they both pull the trigger. Do they see their laser bolts hitting the target at the same time? Well, I'm going to say yes, because I've got no reason to believe otherwise. Okay. So they have another friend called Crater who helps them move the targets around during practice, and he's always keeping an eye out to help them improve their game. He's usually on the move, and his shuttle runs at only 1 speed, which is out of control. So that sounds like he's moving pretty fast. He observes the practice from a different reference frame, so he will possibly have a different take on events. So long as he doesn't turn or otherwise accelerate, his frame of reference is an inertial frame, and his observations are governed by Einstein's postulates. Okay, so that means the speed of light would be the same, and so will the laws of physics. Suppose Crater is heading toward Alyssa with a speed v relative to her. At the instant she fires her laser, with what speed does the laser bolt approach Crater in his reference frame? Okay, so if instead of talking about a laser bolt we'd been talking about the seagull from before, I would incline to give one of these other answers, that the speed would take into account Crater's relative speed towards the object, towards the seagull. But because we know Einstein's postulates here, and they're directly telling us to use them, the speed of light in all inertial reference frames should be the same. Okay, so that seems good. We'll keep going. So now Crater is drawing a space-time diagram as he passes the two girls at speed v. In Crater's inertial frame, it's actually the two girls who are moving with speed v, and to him he's staying still. So he's drawn their world lines in blue here. We've got Alyssa and Bev. Crater calls the time that Alyssa fires t equals 0, so that's this point here, in his frame of reference. At this moment, Crater measures the target at a distance of x over 2 from him and Alyssa's position. So this here is the target, which is halfway between the two girls. In red here is Alyssa's laser shot. So we're being asked at what time in Crater's frame does Alyssa's bolt hit the target. So what is this TA right here? So something else you may want to remember from physics is a relationship between speed, distance and time. Well, time is distance divided by speed. So what distance has the shot travelled? It's x/2, and we'll divide that by the speed it was going. Now it's sort of my intuition to want to do x/2 divided by c, which would be x/2c. That is none of the options. I can't see any reason why it would be c squared, or why would we have this squared here. So I'm going to pick A, and I think just from actually looking at the answers I realise where this c minus v is coming from. So whilst they both measure the bolt to be moving at speed c, according to Crater, the target is moving with speed v as the bolt is catching up to it. So that's why it's not just c on the bottom, but it's c minus v. So now Bev is going to take a shot. According to Crater, does Bev's laser bolt take more time, less time, or the same amount of time to reach the target compared to Alyssa? Looking at this diagram, it looks like that as the shot is going towards the target is getting closer to Bev. So for that reason, I'm going to say it should take Bev's beam less time. Okay, so that one's getting a bit trickier, but I think we're doing all right. So Crater reports to Alyssa and Bev that you aren't firing in sync. So even though he sees the bolts hit the target at the same time, he thinks there's a time difference between when Alyssa and Bev are firing, because he thinks that Bev's beam takes a less time to get to the target. So in order for the bolts to hit the target simultaneously in Crater's reference frame, how long after Alyssa fires does Bev need to pull the trigger? Okay, so you want to find this distance here, which is essentially the change in time that Crater thinks is happening between the time when the girls pull the triggers. So again, time is distance divided by speed. We know from back here that this is the time for Alyssa's beam, and this would differ with a plus sign down here on the bottom for Bev's time. So we really want to do this minus the same fraction except with a plus sign between the c and the v. Might be slightly tricky algebra, so I'm going to take a stab at it. I guess this one, it's the first one. This is the algebra you need to do. So this is Alyssa's time, this is Bev's time. You want to subtract them, which means you need to convert them to having the same denominator as their fractions, and then do the algebra from there. But I think we understand sort of what's going on here. It's the time that Crater perceives there to be between the two girls firing. So Alyssa gets on the comlink and says, "Crater, what are you talking about? We're firing at exactly the same time." And of course that's what it looks like from her reference frame. So puzzled, Crater does an experiment. He performs a U-turn in his shuttle and heads back towards Bev. Now, according to Crater, whose shot will require less time to hit the target? So now he's just going the other way. So I guess it would make sense that things are reversed. And now it would seem like Alyssa's shot takes less time. Yep, so okay. This is sort of seeming a bit strange, and this is relating to the strangeness of simultaneity in special relativity. So if light propagates at the same speed for all inertial observers, as Einstein said, we arrive quickly at some pretty bizarre conclusions. According to Crater, who is moving relative to the target, Bev and Alyssa fire at different times, yet their bolts arrive simultaneous. Perhaps even stranger, the person who fires first switches if Crater changes his direction. So especially at the time when Einstein came up with this, the idea that observers experience events in different order depending on which direction they're moving seems quite absurd. But you know, these calculations of Einstein's theory of special relativity have actually been tested and repeated, and all of it seems to stack up. So these things are true, but there are some very counterintuitive aspects to learning about special relativity. So what we've moved on to here is the topic of causality. So, you know, in everyday life, if a window was opened which made it possible for a baseball to fly into the room, which knocked a lamp off the table and smashed it, then a causal relationship is established. The chronology of these events, or the order in which they happened, must be absolute, mustn't it? So what does it mean for causality in this realm of special relativity, where we've said, you know, the order of events depends on who you are and where you're moving? So we ask, are there any sequences of events whose order is absolute? And we're going to consider events A and B shown on this space-time diagram. So do note that the white line here at 45 degrees through the diagram represents the world line of a light beam. So this is the speed of light represented, and remember its velocity is inversely proportional to the slope, so anything down here, the slope would mean it travels faster than the speed of light, and anything up here less than the speed of light. So what relationship between A and B guarantees that we can find two observers who disagree on their order? So if we take a look at this, the slope connecting A and B is a lower gradient than the speed of light, which would mean it's faster. But it's this answer here that the slope is less than light. What it means for A and B is that they have quite a curious relationship. They have no set ordering in time. Depending on the reference frame we're in, it can be either that A happens before B, A happens after B, or they occur at the same time. So what about space? Is there a frame where these two events occur at the same position? I'm going to go with no here, and that's correct, so let's see why. There is a fundamental separation between the events A and B, in that a beam of light cannot be sent between the two. So their separation in space is greater than the distance that light can travel in the time that separates them. So this separation is independent of the reference frame. So no matter how we tilt the axis or what speed a reference frame is going at relative to them, there is no frame that exists where A and B could appear at the same position in space. For this reason, events like this are called space-like separated, and on the other hand, we have up here time-like separated, which is just sort of by symmetry, where we can always find a reference frame in which they have the same position, but they will never have the same time. It gets kind of cool when we sort of make that diagram look 3D, I guess, by instead of just having one line, world line representing a light beam, we spin that around to be an entire light cone. So here it is still a space-time diagram of, you know, time and space, but we really clearly see the difference between space-like separated events and time-like separated events. So any events that exist within the light cone would be time-like separated. And, you know, if an event happens down here, the speed of light propagates outwards in all directions in this cone, and anything in the future that's within the cone, I guess, can interact with that beam of light. It means that anything in that cone essentially is the future, and anything in an inverse cone is the past. And we can't have any knowledge or interaction with something outside of our light cone. The light cone is all the possible events that can have a physical effect on us. So we're asked a question here: which of the trajectories, A, B, or C, on this space-time diagram is physical? So let's have a look at them. First of all, C, this event here, or this trajectory, would require going faster than the speed of light, because, you know, its gradient is down here with a slope less than that of light. So we're going to rule out C as being not physical. A and B both stay within the light cone, so they could seem, you know, physical, but if you look at it, A actually has a gradient in here which is less steep than that of light, so it too is requiring faster than light travel to reach its destination. So the only really viable one here is be. So I'm going to leave this episode here. I hope that you've learned a couple of things about space-time diagrams and, causality or simultaneous events. Really, I hope that this is just an inspiration for you to want to learn a bit more of these ideas yourself and explore more of special relativity, because it is such a big topic, and to teach you all or even a big chunk of it in a single video is really difficult. But thank you very much for watching, and I'll see you next time.